Hello everyone, I'm here to talk about antiderivatives for my final for Math 312 for Dr. Gillespie's class. Antiderivatives have to do with integral calculus. Calculus itself is broken up into two different categories. You have differential calculus, which has to do with rate of change, and you have integral calculus, which has to do with combination. They both connect through the fundamental theorem of calculus, shown in your flowchart on the presentation. The process of finding antiderivatives is called antidifferentiation or integration. We denote the antiderivative of f as big F, and the derivative of its antiderivative is little f. So if you take the derivative of an antiderivative, you'll get its derivative. The integral sign, which is that little squiggly s in front of that f, is denoted as an integral. So the integral or antiderivative of f equals original function, which is big F, plus a constant, or plus c. So we add a constant because when you take a derivative of a function, all constants equal 0. And this is an undefined integral because there are no parameters to it. So when we take the antiderivative, we have to add a constant. So this creates a family of curves that just have a vertical shift. The second one is just giving you another look at how to do it. So instead of big F and little f, we have g and g prime. So g prime would be your derivative and g would be your original function or your antiderivative. So if we look at the early years of calculus, integration was first thought of or invented by the ancient Greeks of Exodus and Archimedes. Then we moved to Sir John Wallis and Pierre de Fermat, who worked through tangents and also worked closely with trying to find integration, but never put the piece together where integration is the inverse of integrals. Integration is the inverse of differentiation. The ones that actually connected the two was Sir Isaac Newton and Gottfried Lejeune. And they were credited on the invention of calculus. They actually were the ones who founded the fundamental theorem of calculus, which connects the two calculuses. So the fundamental theorem of calculus states that if a function f is continuous on the interval a to b, then the integral a to b of f of x dx equals its antiderivative b minus the antiderivative at a, where f is any function such that f prime equals little f for all x's in a to b. An application of antiderivatives is integrals. We have two different types of integrals. We have definite integrals and indefinite integrals. Definite integrals is represented by the graph on your right, which is bounded by an interval of a to b. An indefinite integral is graphically represented on your left, which it doesn't have any boundaries. The most basic type of integral are constants, just like the most basic equation are constants. So if you take the antiderivative of a constant, you just have to multiply by whatever variable it's respect to and add a constant. So the antiderivative of k of dx equals kx plus c. So if we take the two integrals below, which we have the constants of k equals 5 and k equals 2/3, so the integral of 5 dx equals 5x plus c. And Same goes with if k equals 2/3. The integral of 2/3 dx equals 2/3 x plus c. Now, to explain the power rule, I'm just going to read the function. The integral of x to the n, where n could be any type of number, dx equals x to the n plus 1 divided by n plus 1 plus c, where n cannot equal -1. If n equals -1, that is a special function where it's 1 over x, and that is the special derivative of the natural log of x. So if we take n equals 2, we have the integral of x squared dx equals x to the 2 plus 1 divided by 2 plus 1 plus c. Simplified, that equals x cubed divided by 3 plus c. So trig functions are just like log functions where they have special derivatives. So that means they'll have special antiderivatives. So we know the derivative of cosine is just negative sine. So if we take the antiderivative of sine, it equals negative cosine. And same goes with cosine and sine. So if you take the antiderivative of cosine, it'll just equal positive sine because the derivative of sine is positive cosine. Then if you take the antiderivative of cosecant times cotangent equals negative cosecant. If you take the antiderivative of secant times tangent, it equals secant. If you take the antiderivative of secant squared, you get tangent. If you take the antiderivative of cosecant squared, you get negative cotangent. Now all of these are plus c because we don't have an initial condition, and these are indefinite integrals because you don't have an a to a b. Inverse trig and hyperbolic functions are the same as regular trig functions. They have special derivatives, so they'll have special antiderivatives. So the antiderivative of 1 over x squared plus 1 equals inverse tan. The inverse sine equals inverse cosine. Inverse cotangent in 1 over the square root of 1 minus x squared dx equals inverse sine x. And then so forth and so forth. Next, we'll go to integration by parts. So the formula for integration by parts is the integral of u dv equals uv minus the integral of v du. So you have a antiderivative times by a derivative. So if we take the example of the integral of x times by e to the x dx, we're going to denote our antiderivative, or u, as x, and our derivative, or dv, equals e to the x times by dx. So we find our derivative of u, we'll get du. So our derivative of x is dx. Now we have to find our antiderivative of dv, which is v, and we find our antiderivative of e to the x dx, which is e to the x. So if we put it in our formula, we get the integral of x times by e to the x dx equals x times e to the x minus the integral of e to the x dx. Simplified terms, it equals x times e to the x minus e to the x plus a constant. So if you go to use substitution, it's almost like integration by parts, but instead of the one of the functions being just another function, it's actually the derivative of an inside function. So this is the opposite of chain rule. So if you have the integral of f of g of x times by g prime of x dx, that will equal the antiderivative of f of g of x plus c. So we call it u substitution because we're going to substitute u as your inside function, which is g of x. So du equals g prime of x dx. So your new integral is now f of u. So just take the antiderivative of f of u, which is big F of u, and then just substitute back in u. So substitute g of x back in. Now you can check by just taking the derivative of f of g of x. Now if you go to double integrals and triple integrals, what we have is we're dealing with partial antiderivatives. So partial antiderivatives is the inverse of partial derivatives. So what it is you have multiple variables and you take only one variable, which is denoted in this case in the inside of dy dx. So the first one you're going to do is dy, so respect to y. And then every other variable is considered a constant or a coefficient if it's multiplied by the variable. So how to solve double or triple integrals are you work inside outward. So for this case, the integral of a to b, the integral from c to d of f of xy dy dx, first you take the partial antiderivative of y and then evaluate it from c to d, and then you take the partial derivative of x denoted by a to b. The same with the triple integral. So in this case, the integral from a to b, the integral from c to d, and the integral from r to s of f of x, y, z, dz, dy, dx equals, you first do the partial derivative of z and evaluate it from r to s, then you take the partial derivative of y, evaluate it from c to d, and then you take the partial derivative of x respect to a to b. Applications of integrals. One application is finding the area in between two curves. So we'll denote the two curves as f of x and g of x. On your right, you have two graphs where f of x is your top curve and g of x is your bottom curve. On your left, you have an area or a region that is bounded by f of x in the x-axis. So that's y equals 0. So that's your second curve. Now, because the area is bounded by an axis, you have the area equals the integral of a to b of f of x dx. Now, on your right, you would have area equals the integral from a to b of your top curve, which is f of x, minus your bottom curve, which is g of x of dx. Now, another application is finding arc length. So we have two different types of arc lengths. We have parametric and we have croissant. And then so we denote arc length as L. So L equals the integral of a to b of the square root of dx dt squared plus dy over dt squared dt. And also L equals the square root of a to b of the square root of 1 plus dy over dx squared dx. Now this is where y equals a function of x. Now if x equals a function of y, L equals the integral from c to d of the square root of 1 plus dx over dy squared dy. Another application would be finding volume. So in this case, dV equals the surface area of the cylinder times the thickness of the shell. So we have a region that's bounded by the x-axis and the y equals f of x from a to b. And we're going to rotate it around the y-axis, making this cylindrical looking thing. So in proper terms, this creates shells, cylindrical shells. So if you go down the process, what we have is the area. So that goes into the perimeter of the base of the shell times by the height of the shell, which equals 2 pi radius of the base times by y dx. That is 2 pi times by x times by y dx, which equals 2y x times by f of x dx. So the volume of a solid S is as follows. The volume equals 2 pi, the integral from a to b of x times by f of x dx. Another application, a real-world application, would be through physics and engineering. So we can find work through that. So work on variable forces, work on stretching a spring, work on lift of a cable, work on emptying a tank, work on hydrostatic force on a dam. So these three graphs represent different works as area under the force curve. So the first one, the force curve is constant, so it's just a box, and we know the area of a rectangle is just length times width, or height times x times y. Then we have a linear function, so that creates a triangle, so we just take 1/2 the base times height. Then we actually have a curve. That's when we actually use our integral. So this one goes from 0 all the way to x, so we have the integral from 0 to x of f of dx. Another real-world example would be through economics in consumer surplus and producer surplus. So in this example, what we're trying to find is consumer surplus and producer's surplus. So from the graph right there, first we have to find the equilibrium point, which is Q naught, P naught, Q naught. So we have the two functions equal to each other to find Q naught. And then once we find Q naught, we can find P naught. Now, the consumer surplus is given as CS equals the integral of 0 to Q naught of f of Q minus P naught dq. And then the producer's surplus is given as PS equals the integral of 0 to Q naught of P naught minus G of P dq. One of the last applications would be probability or in stats. So we use integrals to find the variance, we use integrals to find probability. So finding the variance of x, we'll get the integral of negative infinity to positive infinity of x minus the exponentiation of x squared, quantity squared, times by f of x dx. So we take the example where the exponentiation of x equals 1/3 and f of x equals 2 times by 1 minus x. So we have the integral of 0 to 1 of x minus 1/3 quantity squared times by 2 times 1 minus x dx. So if you go through the process of simplification, you'll get down to bringing out your constant of 2. So 2 times the integral of 0 to 1 of negative x cubed plus 5/3 x squared minus 7/9 x plus 1/9 dx. So all you have to do is take its antiderivative. So each one of these are just considered powers, and you have one constant at the end. So with that saying, you get the antiderivative of 2 times negative 1/4 x to the 4th plus 5/9 x to the third minus 7/18 x squared plus 1/9 x, evaluated from 0 to 1. Now, because every term has an x, the 0 will just be minus 0. So we don't have to really deal with the 0. So we're just going to deal with the 1. So if you plug in 1 for all of the x's, you get 2 times negative 1/4 plus 5/9 minus 7/18 plus 1/9. And all that equals 1/18. An example of the probability density function is f of x equals the probability of a, x is in between a and b, which equals the integral of a to b of f of x dx. But that has to be greater than or equal to 0. These are my credits, and I do thank you for watching.